Welcome to everyone to this seminar. Today the speaker is Bhanu Kumar. I'm very happy to present him, also because I know him. I met him several times here in Italy, and he will speak about rapid and accurate computation of invariant tori manifolds and connection near mean motion resonances in periodically perturbed planar circular restricted three-body problem models. Whew. Okay. Please, you can start. Thank you.
Okay, thanks for the introduction, Giulio. So as I mentioned, this talk, I'm going to be talking about the computation of tori manifolds and connections near resonances and periodically perturbed planar circular RTBP models. This is joint work with my advisor, Rafael de la Llave at Georgia Tech, and my mentor at JPL, Dr. Rodney Anderson. So there we go. Okay, so just a little bit of motivation for this work. In the planar circular restricted three-body problem, we have unstable resonant periodic orbits, which are important for transport within interior and exterior realms of motion. So essentially, that's say if you have the Sun-Jupiter system, then changing your your semi-major axis, or in the exterior realm outside of the Sun-Jupiter system, changing your semi-major axis there, these orbits are important. And we've done work earlier on the computation of the orbits and their stable and unstable manifolds around these resonances. But when you add a periodic perturbation of the planar circular problem, these unstable resonant orbits should persist as 2D invariant tori in the extended phase space, R4 cross T. And we think that homoclinic and heteroclinic connections between these tori can result in changes of three-body energy and Arnold diffusion. So that's why we decided to study this problem. So just a little bit of background. Most of you should be familiar with the planar circular restricted three-body problem. In this, we have the primary and secondary bodies M1 and M2, the mass ratio M2 over M1 plus M2, and M1 and M2 just follow a circular Keplerian orbit around each other, around their barycenter. And then we consider the motion of a spacecraft with negligible mass and its position xy in the plane. And the equations of motion for the spacecraft are Hamiltonian, and energy is conserved along the trajectories. This H sub O is the Hamiltonian, which is preserved along the trajectories in the planar circular problem. Of course, this is the basic configuration that we consider. So now there's a lot of different interesting periodic perturbations of the planar circular problem. For example, you can talk about restricted four-body models like the bicircular, coherent quasi-bicircular, and Hill-restricted four-body problems. The perturbation that we're going to consider is the planar elliptic restricted three-body problem. We're going to test all our tools on that model. And just the general form of such periodically perturbed systems is where you have a perturbation parameter epsilon and a perturbation phase theta sub p in a frequency big omega sub p, such that the perturbation phase theta sub p advances as the constant rate big omega p, and then h sub epsilon is just h sub o plus h sub 1, where h sub 1 vanishes for epsilon equals 0. So now, and of course here h sub 0 depends only on xy and the conjugate momenta, not on the phase of the perturbation. So now in the planar elliptic problem, which we're going to use as our test case, M1 and M2 follow elliptic orbits instead of circular. So that's the only change from the circular model. And we always scale time so that the period of M1 and M2 is 2 pi, so that big omega sub p, the phase of the perturbation, is 1. And so we can consider theta sub p to equal time modulo 2 pi. And the coordinates of M1 and M2 in this model lie on the x-axis with the origin at the barycenter, but the distance between them is time periodic, which introduces the periodicity. And the Hamiltonian here is h sub epsilon given here, which is a time periodic Hamiltonian, because n of t and e of t are the angular rate and eccentric anomaly of the M1, M2 orbit, which are periodic with period 2 pi. So now just a quick overview of what resonant periodic orbits are. These are orbits, periodic orbits in the planar circular problem, which are not associated with Lagrange points. The periods are basically those that are almost resonant with that of the M1, M2 orbit. So basically approximately rational multiples of 2 pi in the units that we're using. And the notation we use is that an m to n orbit means that the spacecraft makes m orbits for every n orbits of m1 and m2 around each other. And we know that there's a stable and an unstable resonant periodic orbit at every energy level, or at least for a range of energy levels at every given resonance. And the eigenvalues of the unstable resonant periodic orbit are just 1, 1, and then a stable and an unstable eigenvalue, which are reciprocals of each other. And we know that these unstable orbits have 2D stable and unstable manifolds in the planar circular problem, and heteroclinic connections can exist as well. And we also can see that these periodic orbits should persist primarily as 2D quasi-periodic orbits when you add in the perturbation, a periodic perturbation, in the extended phase space. And the way to think about this is just that if you take all of these unstable resonant orbits around a given resonance across energy levels in the planar circuit problem, this forms a normally hyperbolic invariant manifold. And we know that these persist under small perturbation, and the dynamics inside also, the existing invariant circles should remain as tori in the extended phase space due to KM theory. So this is just a picture of what some of these 3-4 unstable resonant orbits look like in the Jupiter-Europa system in the configuration space. So in this study, our goals are to consider periodic perturbations of the planar circuit problem. The tools we develop are more or less entirely general. And so the tori, which the planar circular problem resonant periodic orbits persist as, we want to develop a Quasi-Newton method to solve for not just the tori, but also their center stable and unstable directions. Then we want to implement the continuation by epsilon as well as rotation number. We want to compute Fourier-Taylor parametrizations of the stable and unstable manifolds, globalize them after regularization, and then finally find and then accurately compute the homoclinic and heteroclinic connections between the tori. So now, just before we start talking about the computation of the tori, I want to define the stroboscopic map. So as mentioned, in the extended phase space, we expect to have two-dimensional invariant tori, where this can be parametrized as a function of two angles, theta and theta p, where this function k2 has the angles theta advancing at some constant rate, big omega 1, and then theta p is the phase of the frequency of the advances at the frequency of the perturbation, big omega sub p. And we know that because one of the frequency of the perturbation is big omega sub p, so one of the angles should advance at that rate in the torus. So now we define the stroboscopic map, big F, as being the time 2 pi divided by big omega p mapping of extended phase space points by the equations of motion. Of course, after fixed, and if we map any point k2 of theta and theta p by this map, because we're just advancing everything at 2 pi divided by big omega p, theta p comes back right where it started. So, and theta advances by this constant amount, little omega. And the thing to note here is that since theta sub p goes around by a full 2 pi, it comes back where it starts. So the phase angle of the perturbation is invariant under big F. And so that second angle of the parametrization is invariant under big F. So if we just fix theta p, in my case, I always fix theta sub p equals 0, and then define k of theta equals k2 of theta and that fixed angle theta p, that's just a circle now, a function of one angle theta. And it's a lot less difficult to find a one-dimensional invariant torus, which is just a circle of a map F in the four-dimensional phase space, x, y, px, and py, than is to find two-dimensional tori of a whole flow in the extended phase space. So that's exactly what we do from now on. So considering the stroboscopic map, we assume that the frequency of the other angle, big omega 1, is known from the planar circular problem. And this is known if you know the period of a periodic orbit that you're trying to continue into the perturbed problem. And now we want to find parametrizations k, p, and big lambda, which are, k is a vector valued function of an angle, and p and big lambda are matrix valued functions of an angle, such that equations 1 and 2 here are satisfied. The first equation just means that F maps points of k onto translated points of k. And the second equation here you might be less familiar with, that all this is saying is that df maps the columns of p onto the columns of P combined in the fashion dictated by the matrix lambda. And this big lambda matrix we declare should have the form given right here. So as you can see, it's almost diagonal. So what it's saying is that df should effectively scale the columns of P by the factors along this diagonal, except for the second column will get sheared by this T. And basically how this works is that the big matrix P, its columns should be dk, the center direction at k of theta, and the stable and the unstable directions at k of theta. If you do this, then you can see very easily that the relation 2 should hold. So essentially equation 2 is necessary to solve for the centers, stable and unstable directions at each point of the torus. So now, of course, as shown here, the entries of lambda are all fixed except for the third and fourth diagonal entries and the row 1 column 2 entry. So now we assume that we know an approximate solution of this, and this is true when you're doing, for example, numerical continuation from the planar circuit problem. And we define the errors. So E of theta is the error in equation 3, and then irreducibility is essentially the error in equation 4, except for the multiplying through by P of theta plus omega. And so now we want to find corrections, delta K, delta P, and delta lambda. So first of all, let's start with delta K. So if you linearize, you get this equation 5 here. And now if this equation 5, if you want to solve it directly for delta K, what you have to do is you discretize theta on a grid of n points and then solve it for delta K at all of those n theta values simultaneously. And doing that requires a large linear system because you're solving for, in our case, the phase space is 4-dimensional, so you have a 4n by 4n system. So if you want to use like just a Newton method on that. So instead of doing that with this huge linear system, instead, what we do is we take advantage of this equation 4 here, assuming that it has a small error. And what you do is you define delta K equal P times xi, and then equation 5, you just can almost diagonalize by multiplying through by P inverse of theta plus omega, because what you see happens is that delta K gets replaced with P xi, and this on the left of df is multiplied by P inverse of theta plus omega, which just is approximately equal to lambda. So that P inverse df times P gets replaced by this lambda plus irreducibility, and irreducibility times xi is quadratically small because xi is going to be approximately of the same order of magnitude as E, so we ignore it. And then, since of course lambda is almost diagonal, Gaussian elimination is not required. In fact, if you just define this eta of theta as being negative P inverse of theta plus omega times E, what you have to do is you get these 3 equations here for xi1, xi2, and xi3, and xi4. And you can see that the equations for xi3 and xi4 and xi2 are entirely decoupled from each other. And the equation for xi1 is also only involves xi2, and xi2 can be solved separately, plugged into the equation for xi1, and then you solve xi1 independently. So no Gaussian elimination required. Xi3 and xi4 can solve by just iterating contraction maps to convergence by the Banach fixed point theorem. So you start with, say, xi3, xi4 equals 0, just iterate this until it converges, you get the solution of the equations. Xi2 and xi1 are just found solving the usual cohomology equations that are very, very common in KM theory. And for this, of course, you just express everything in Fourier coefficients, and then you get these 2 expressions. You can see that if you want them to be equal, then the Fourier coefficients of A should just be the Fourier coefficients of B divided by 1 minus e to the ik omega. So solving these, and of course here we assume that omega is sufficiently Diophantine that all of this converges. Of course, this can require some trial and error with checking which rotation numbers work in the system. So now once xi has been found, you of course set the new k to be equal to k plus p xi. You set the first column of p equal to dk. You recompute the df and the reducibility error at the new k of theta. And then finding delta p and delta lambda follows very similar methodology. You linearize, and then you plug in p times q for delta p, and then ignore quadratically small terms that are products of errors and deltas. And what you end up with is this equation right here. And again, this is just going to be basically almost diagonal, and you can you end up with several decoupled equations that are solved using the same methods as we did for finding xi, contractions and cohomology equations. And then finally, you can set p equal to p plus pq, big lambda equal to big lambda plus delta lambda, recompute the errors, and keep going until the errors are within tolerance. And the thing here is, since we avoided the Gaussian elimination, the complexity of the method is order n log n rather than order n cubed. And not only do you get the torus, but you get the stable, unstable, and center directions at each point of the torus as well. So advantageous in more or less all the different ways. So now, of course, we want to use this method for computing tori. So we use this method when we're doing continuation by epsilon, right? So you start, of course, with the epsilon equals 0 system, which is the planar circular. Huh? Somebody saying something? Okay. So you start with the periodic orbit, which has, say, a known period, big T sub p, from the epsilon equals 0 planar circular problem. And then you take a point x sub o on the periodic orbit, and let's say that phi represents the flow map of the planar circular problem. So now if you want to set up the initial k of theta, what you do, if the stable and unstable eigenvalues are positive, then you just take evenly spaced points on the periodic orbit as your k of theta. Otherwise, if the eigenvalues are negative, you have to loop around twice just in order to have the bundles oriented properly for the equations to be solved later. And so if now you let m of theta, define this matrix m of theta, which has the eigenvectors, the unit eigenvectors of the monotony matrix at each point k of theta. Since this is a periodic orbit, this is perfectly well defined right now. And these should just be the eigenvectors corresponding to 1, 1, lambda s, and lambda u. So the columns 1, 3, and 4 of P are just going to be the same, essentially, except for you have to make sure they're oriented continuously. And then column 2 is a little more complicated because it's the center direction. And so, but we don't want just any center direction. We want one that satisfies that very particular form of big lambda. So for that, that's known as a symplectic conjugate. Those familiar with symplectic geometry and Hamiltonian systems would probably know more. But essentially, you can find this and you can show that this formula works. If you multiply dk by J inverse, normalize it, and then essentially project it onto only the center components of only the center subspace. And by projection, this isn't quite like a dot product type of projection, but it's following this formula that's shown right here. So now that we have an initial k of theta and a p of theta, and then lambda is just found using the formula p inverse of theta plus omega df times p, we can now implement the method. And so we need to do this on the computer. So we discretize k, big P, and lambda as arrays of function values on evenly spaced angles. So theta sub I is just 2 pi I divided by n, and I goes from 0 to n minus 1. And we store the values of k, p, and lambda on these theta values. Then, if remember, we had in our method many different operations, some of which are carried out well on the grid of function values, but others are better carried out in the Fourier space. So for that, we can use FFT. So for example, if you want to translate the function, you take FFT, and then you multiply each Fourier coefficient by e to the ik omega, and then you take the inverse FFT to find a of theta plus omega and its values at theta sub I. And then same thing with differentiation, except for you multiply the Fourier coefficients by ik, and then take the inverse. So now, just a few notes about issues that arose when discretizing the method on a computer. So one thing that you might see is, of course, in continuous ideal case, it's not an issue, but on the computer it ends up being that applying this algorithm for translation, if you first multiply two functions, and by functions I mean their values on the grid of theta values, and then translate, this ends up being possibly slightly or even more different from first translating the two function values and then multiplying. Now, the second problem that arose was that sometimes translating function values forwards and backwards by the same amount change the function values, which of course in real functions and continuous, when you're talking about continuous functions, is not the case. And so the solution we found is that both of these issues arise primarily when the high order Fourier coefficients are larger. And of course, in reality, we don't expect that the solutions should have larger high frequency Fourier coefficients, but just for some numerical reason, it happens when you're doing this method. So the solution was, we found, just to run the K and the P, or their discrete representations as arrays, through low pass filters whenever the method starts breaking down or between continuation steps. So this solved our issue, and we were finally able to continue many tori all the way. And the third problem that arose was the continuation sometimes would start requiring excessively small step size. And this was especially the case when we were continuing by rotation number. So fixing the epsilon and changing the omega and trying to find a family of tori, and especially when we were getting closer to the singularity. So the solution to this we found was to make the shear term t of theta constant. And the reason we can do this is that column 2 of P is just the center direction of the torus at a given point k of theta. And so you can add, and dk is also in the center manifold of the torus. It's just a tangent to the torus. So you can add any multiple a of theta times dk of theta to the second column of P without affecting big lambda, except for the shear term t of theta. And so we choose an a of theta, which kills the variation of t of theta. And you can show that this just involves solving a cohomology equation. Just a of theta minus a of theta plus omega is equal to negative t of theta minus its average. And we have to take away the average because you can see on the left-hand side, the constant terms of a, when you talk about the Fourier coefficients, are going to cancel out. So you cannot have any constant term on the right. That's why we subtract the average. And doing this, solving for a, and then adding a of theta times dk of theta to the column 2 really improves the numerical stability of the Quasi-Newton method. So that's just another numerical curiosity that's worth doing. So just a few pictures. We continued some tori by eccentricity in the planar elliptic restricted three-body problem from the planar circular problem. So this is in the Jupiter Europa. We continued a 5-6 unstable resonant orbit to its corresponding torus. The eccentricity of the Jupiter Europa orbit is 0.0094. So this is a zoomed out view. And then zooming in, you can see that basically what's happening is that the torus is moving leftwards as eccentricity increases. And that's to be expected because Europa itself moves leftwards as eccentricity grows higher in this case. And then, of course, here we, instead of continuing by eccentricity, we fix the eccentricity to the physical value of the Jupiter Europa system, 0.0094. And then we continue by rotation number to get a family of tori. And so you can see a lot of tori zoomed out here. And now zooming in, you can see again that we have lots of tori. And in fact, we were able to use our method to continue them to this little red circle on the left, which is Europa, which of course is a singularity of the equations of motion. So we were able to successfully use this method to compute many tori. So now, of course, we have the tori and we have their stable and unstable directions at each point k of theta. So the next natural step is to find the invariant manifolds of these tori. So we know that these tori are invariant circles, 1D, just T. And so their stable and unstable manifolds are going to be topologically equivalent to cylinders, T cross R, under the stroboscopic map. So now, from now on, we assume that lambda S and lambda U are constant. It's easy to modify P and lambda so that this is true. The method is given in the paper cited below. And so now the invariance equation for the manifolds we're trying to compute is just that f of w of theta and s should equal w of theta plus omega times lambda and lambda s. So what's happening, you map points of f of w by f, and you get a different point of w except for translated by omega, and then the real parameter is scaled by lambda. And so now what we want to do is we want to parametrize w of theta and s using a Fourier-Taylor series. So of course, s is the, I guess, the parameter in the stable and unstable directions, and then theta is along the torus. So the constant term of this Fourier-Taylor parametrization is going to be k of theta. And when I say constant, that's constant in terms of s, right? So the s to the 0 term is k of theta. And then we want to find the s to the k for k greater than or equal to 1 coefficients. So the thing is, w sub 1, the s to the 1 terms of this parametrization are already known, actually, because we have columns 3 and 4 are the stable and unstable directions at each torus point. So now we need to find k equals 2 s squared in higher order terms of this parametrization. So we want to find w sub k for k greater than or equal to 2. And we can do this recursively by assuming that the invariance equation and w of theta and s are solved to degree s to the k minus 1. And what you do is you find the order k error in the equation. So w less than k here is just the parametrization up to order s to the k minus 1. And so you find the error in the equation using this truncated series to order s to the k minus 1. And then you find the s to the k coefficient of this error. And then you solve for w sub k s to the k, which cancels out this error. So essentially, the equation to solve this for w sub k is given here. And due to this lambda to k, since k is greater than or equal to 2, this is you can rewrite this as a contraction mapping, which can be iterated to convergence to find w sub k. And then finally, once you have w sub k, you add it on w sub k s to the k to the lower order terms, and then you repeat to find this entire procedure to find the higher order terms. So we've done this for up to maximum s to the k value of k equals 5, but we can definitely go higher than this. So now one thing I glossed over here is this error e sub k. How do we find it? Because f is a mapping by a flow, and w less than k is a Fourier-Taylor series. And even if you fix theta, it's a polynomial. So how do you map a polynomial by a flow? So for this, two tools are necessary. First of all, we have automatic differentiation, where you can recursively evaluate and operate operation on a polynomial or on set of polynomials. So for example, if you want to divide two polynomials, let's say that you know the coefficients of f and g. In fact, this isn't just polynomials, but more even for like formal series. What you can do is you just multiply them, and the usual formula for the s to the k, x to the k coefficient of f of d times g is here, and then rearrange it, and what you get is this formula for the x to the k coefficient of the quotient. And what you can see is that it only involves the known coefficients of f and g, as well as the lower order coefficients of the quotient d. And we know the d to the d sub 0, the constant term of the quotient d, that's just the quotient of the constant terms of f and g. So we can recursively use this to find the higher order terms of the quotient polynomial. And in a very similar way, these kinds of formulas exist for powers and many other functions as well, and they're all given in this book, which has been very useful for this study. So now, if you want to propagate a vector of polynomials by the flow, all you have to do is, first of all, you fix the theta values to be theta sub I, the different values on the grid, and you do for each theta sub I separately. So fix theta sub I, and then substitute the polynomial in S, w less than k of theta sub I and S for x, y, px, and py in the equations of motion. And then you can simplify this using automatic differentiation formulas to get polynomials in S for their time derivatives of x, y, px, and py. And the way to interpret this is that this resulting polynomial, its coefficients are just the time derivatives of the polynomial coefficients of each component of w less than k of theta sub I and S. And so using this essentially differential equation in polynomials, you can just integrate the polynomial coefficient by coefficient to get the stroboscopic map F applied to W less than K of phase sub I and S. And of course, one thing to note here is that if you're integrating a degree D polynomial and you have n-dimensional states, then the integration required is going to be n times d plus 1 dimensional. And you have to do big N, where that's the number of discretization points of theta for that many theta values. So, but it can be done, and it can be parallelized as well across the theta values. And so we can do our parametrization method for the manifolds. So once the manifolds are computed, of course, in reality, we can't compute an infinite series, so we have to stop our computation at some point. So these parametrizations are going to be not exact, right? So of course, we go for k greater than 1 because we want higher order terms of the polynomial of the Fourier-Taylor series. But we want to find how far we can stretch S before the parametrization is no longer valid. So let's say we want an error tolerance of 10 to the negative 5. What you do is you want to find the maximum absolute value of S so that for all the theta values, the error in the equation f of w minus w of theta plus omega lambda S is less than the tolerance. So you just test, you make S bigger and bigger and see where it breaks down. It violates the error. And what we found was that if you do k equals 1 versus k equals 5, you see a 50 to 200 times improvement just by adding on those 4 coefficients to the parametrization. You can make S up to 50 to 200 times bigger if you compute those extra terms. And so for the linear parametrizations, we had domains of roughly 10 to the negative 4, 10 to the negative 5, versus for degree 5, it was 10 to the negative 3 or 0.01. So, and even for the smaller S values than these maximum fundamental domain values, we expect to have better accuracy. So this maximum absolute value of S, we call the fundamental domain big D. So now, of course, we also want the parametrization values, the values of the manifold W of theta and S for S outside the fundamental domain. So just applying the equation that essentially defines the values of W of theta and S, what we can use is this formula here for lambda greater than 1, because what you do is essentially you choose k large enough so that lambda to the negative k times S is within the fundamental domain of the parametrization, evaluate the parametrization there, and then just apply the stroboscopic map F k times, which is just numerically integrating by k times the perturbation period. And then same thing if lambda is less than 1. In this case, you have to integrate backwards, negative k times, and k is computed so that lambda to the k times S is within the fundamental domain of that parametrization. So one thing to note is that if you have resonances with instantaneous semi-major axis close to 1, the manifolds can actually pass through the singularity at M2. So globalization using these formulas can require a Levi-Civita regularization of the M2 if this happens. Of course, we're not dealing with the planar circular problem here, so a little bit of modification is required. You just have to add an extra angle and the conjugate momentum before you derive the generating function and the transformation. So just in the interest of time, I'm not going to go over that, but I can talk about that later if you would like. So here's an example of what one of these manifolds looks like when it's globalized out somewhat. So now that we have the value, a method of finding WU and WS unstable and stable manifolds accurately, what we want is to find connections. So the first step in this is that we represent the manifolds as meshes by computing WU and WS, let's say the unstable and stable manifolds, at discrete grids of theta and S values. So you just take, of course, the theta values are the ones that we had earlier, 2 pi I divided by n for I from 0 to n minus 1. And then you compute for different S values. You start out, let's say, at a grid of S values, and then you propagate those S values outwards and you get a non-uniform grid of S values as well. And what you then can do is you connect the points of the manifold of consecutive theta and S values. So you get a mesh of quadrilaterals in 4 dimensions, right? So the schematic view of this is given here. And then what you can do is, of course, finding intersections of quadrilaterals. Well, in 4 dimensions, that's not even necessarily well defined. But what you can do is connect the diagonals to form triangles. And now this is well defined, that each triangle represents a plane in 4 dimensions. And the problem of searching for heteroclinic connections between these manifolds just becomes the problem of finding intersections of triangular meshes in 4D space. And of course, this is parallelizable, but it's still better to try to cut down the search as much as possible. So now, of course, for this, we can revert to the dynamics a little bit to restrict our search. So define these sets, which we call layers, as being the set U sub n and S sub n. So U sub n is just, you take all the points W sub 1 on the unstable manifold at theta and S, where theta can be any value on the torus, and S lies within these intervals as given here, where D sub U is the fundamental domain of that parametrization. So, and then you just take lambda sub, multiply that by lambda sub U to the n minus 1 and lambda sub U to the n. And the key thing to remember is that F maps points with S to the lambda sub U to the n minus 1, 2 points with lambda sub U to the n. And then you do this very similar thing for the layers S sub n, where theta is any value and S is between the fundamental domain D sub S of the stable parametrization, divide by lambda sub S to the n minus 1 and lambda sub S to the n. And as mentioned, the important property of this is that the upper end of the interval is mapped to the lower end of the interval by F or by F inverse, depending on whether it's the unstable or the stable layer. So F of U sub n is just going to be U sub n plus 1, and F inverse of S sub n is just going to be S sub n plus 1. So now let's say you have a point in the intersection of the manifold layers U sub m and S sub n. If you iterate that by the map F, F of x, which is also an intersection of the manifolds, is going to be in U sub m plus 1 intersecting S sub n minus 1, and then so on and so forth. Iterating again, it's in the intersection of U sub n plus 2 and S sub n minus 2. But what you can see is that the sum of the layer indices is always m plus n. And of course, if n plus 1 is n is even, you can see that by iterating this point backwards or forwards enough times, you can end up so that this trajectory is in the intersection of a pair of layers with the same index or with indexes that are only one different, right? So if the sum is even, then you just iterate backwards or forwards until you have something like U sub n, S sub n, or if the sum of the indices is odd, you just iterate backwards or forwards so that you have indices such that it's U sub n and S sub n plus 1 or something like that. So, and of course, it doesn't matter which point on the trajectory we find, as long as we find one of them. So we don't need to search for all the different pairs of layers. We just search for the pairs of layers of the form just mentioned. So, so for example, in this picture, you would check if U sub 3 intersects S sub 3 or S sub 2, and then if that you'd see no intersections there, then you would go to U sub 4 and check if that intersects with S sub 4 and S sub 3, but you wouldn't need to check whether U sub 4 intersects S sub 2, because that'll have been taken care of by the previous checks. So now that we have managed to restrict our intersection search, what we want to do is still, these layers are represented by triangular meshes by the same division of the quadrilaterals as earlier. So what we need to do now is check every triangle on one of the layers with every triangle on the other layer mesh and see if they intersect. So of course, since these are 2D triangles in 4D space, they're going to intersect at isolated points. So of course, if you have x1, x2, x3, and y1, y2, y3 as the vertices of the two triangles, then you can test for intersection precisely using this basic linear equation You solve for the constants a, b, c, d, or yeah, you solve for the variables a, b, c, d, and then the triangles will intersect if a, b, c, d are all non-negative, and a plus b is less than or equal to 1, and c plus d is less than or equal to 1. So it's a simple test, but it's not simple enough to be so efficient when doing it on the computer. It's still computationally expensive due to the solution of a linear equation. So to solve this, we first pass all of these triangles through a fast rejection test. And then we only apply the precise test to the pairs which are not rejected. So a basic test for this is schematically represented here, that you basically are making a box. This is 2 dimensions, but it works the same way in 4 dimensions. Draw a box around the 2 triangles, and then reject the pair of triangles from intersecting if the boxes don't intersect. And all this means, I guess, arithmetically speaking, is you check all the x coordinates of one triangle, check and see if the maximum of those is less than the minimum of the other x coordinate of the other triangle. And you can do this with each of the coordinates, and that's what's represented in this picture. In fact, you don't even need to do this with triangles. You can do this with quadrilaterals as well, right? So you check if the maximum x coordinate of one quadrilateral is less than the minimum x coordinate of the other quadrilateral. And if the 2 quadrilaterals don't intersect, then you know that the triangles within those quadrilaterals can't intersect either. And in fact, we end up, our own rough test ends up using quadrilaterals to check for triangles just to save some memory, because otherwise we were running out of memory. So this bounding box test only uses greater than, less than, and operations. So it's much simpler computationally than the than the triangle intersection using the linear system, but still it needs to be carried out on a very large number of triangle pairs. So for example, if you have 1024 theta values and 35 s values in a layer, then you have about almost 5 billion pairs of triangles to check. And even if you use the quadrilaterals just in order to save memory, as I mentioned, still you only divide by 4, it's still 1.2 billion pairs of triangles to check. So I implemented this algorithm with about 2.4 billion quadrilateral pairs in MATLAB, and operations on 4D arrays and 4 CPU cores, and it parallelizes everything, and still takes about 7.5 to 8 seconds just to check a pair of layers like that. So, however, the thing is that this procedure is extremely parallel. You're just doing this same simple operations on huge number of pairs. So it takes a while on the CPU, but it's something that's actually very perfect for a graphics processing unit, which we call GPUs, since those have huge numbers of threads, which aren't by themselves that fast, but there's a huge number, so they're perfect for this purpose. So of course, we first looked at if we could do this in MATLAB, but MATLAB's limited to NVIDIA CUDA GPUs. And then I had access to JPL's high performance computing platforms, which have NVIDIA GPUs, but they don't have MATLAB. And my own laptop has MATLAB, but only an AMD GPU. So a little bit of a bind. So what's the solution to that? Yeah, so hopefully that makes some people laugh. So we switched from MATLAB to using the programming language Julia, and we implemented this algorithm in Julia using the OpenCL library. And again, as mentioned, in order to fit into my laptop's video RAM, we had to use quadrilaterals, which decreases the number of pairs to check by a factor of 4. And by doing this bounding box test on the laptop GPU, in fact, just in general, I guess we have several different things mentioned here. For 2.4 billion quadrilateral pairs on the bounding box, we found that it took about 30 seconds on a single CPU thread. This was the same both on my laptop and on the JPL supercomputer. It took about 7.5 to 8 seconds on my laptop's quad-core CPU. And then if you use my laptop's GPU, it's about 3 years old. It's a good GPU, but it's not super fancy. It took 0.2 seconds. So that's like a, 40 times improvement there. And then on the JPL supercomputer GPU, it took 0.02 seconds. So a massive speed up there of this bounding box test. And just for the sake of completeness, we did try the CUDA, the Julia CUDA library as well. It's a lot simpler to code Julia CUDA because it has a lot of high-level capabilities. You don't have to get down and dirty into actually programming GPU kernels there. But it was a lot slower, about by a factor of 10 to 20. So we just stuck with the OpenCL library, even though it was harder to code. And then what we found, just kind of checking, is that the bounding box test rejected 99.85% of the quadrilateral pairs, which of course then makes it much faster to run the precise test on the non-rejected pairs. And then the runtime of the precise test is usually less than 0.1 seconds, especially when almost all the pairs are rejected. And it was always less than 0.55 seconds. So checking a pair of layers in this case was generally like less than 0.3 seconds, and then always less than 1 second. So a huge improvement there from earlier. So just this rough triangular mesh search, we found a lot of rough intersections. So keep in mind here that the manifolds are being represented as triangular meshes. So you're essentially linearly interpolating between a grid of points. So these manifolds are not that accurately represented yet. So we end up with a lot of different intersections between these triangular meshes, which are shown as the yellow circles in this picture, projected into the XYPX and XYPY spaces, because really we're dealing in 4 dimensions. So now we want to find, since as I mentioned, these triangular meshes are not 100% accurate. So we want to find these connections more accurately. And the equation to solve for that is just given right here, where you want to find theta u, su, theta s, and ss, such that wu at the u values minus theta ws at theta sub s and s sub s equals 0. So now, of course, the intersections we have give approximate solutions, theta sub u, theta sub s, s sub u, and s sub s to the equation. We found that the error in this equation was generally about 10 to the negative 2, 10 to the negative 3 for the solutions we found in this picture right here. So now we want to differentially correct the solutions found for the mesh search. So what we need to do is we need to compute the differentials of the parametrizations w sub 1 and w sub 2, w sub wu and ws at theta u, s sub u, theta s, s sub s. And keep in mind that for s sub u and s sub s large enough, we can't just directly use the polynomials, the Fourier-Taylor series we had earlier. So here I'm just going to do it for wu. The ws works the exact same way. You have the formula that we stated earlier for wu, which is just for k large enough, fk of the wu evaluated at the point k steps before. And so taking the partials with respect to theta and s of this equation here, what you end up is df to the k evaluated at a point with a smaller s value. So we, of course, take k large enough so that lambda sub u to the negative k times s is within the fundamental domain of accuracy of the parametrization. So now that lambda sub u to the negative k s is small enough, we can evaluate w sub 1 there, and then find df to the k at that point, where of course dfk is just the essentially it's a state transition matrix, which you can find using variational equations. And then partial w1, partial theta evaluated at that theta and lambda sub u to the negative k times s. That's the differentiation of a Fourier-Taylor series, because for this small enough s value that we have, it's valid. So that's just found using Fourier-Taylor series. The other df to the k is found using state transition matrix. And then the partial with respect to s is, again, you have the df to the k, which, as I mentioned earlier, is a state transition matrix. The partial w1, partial s is, again, just found by differentiating a Fourier-Taylor series with respect to s, so polynomial differentiation. And so after you find these partials, that gives you the derivative with respect to theta u and s sub u, and then same with theta s and s sub s if you do the same thing using the formula for ws. And then we successfully use this to differentially correct several solutions of this equation to errors on the order of 10 to the negative 8. So here's an example of what happens with this method. And what we had to use a damped Newton method, and I'll explain that in a second why we have to do it. So here I've labeled the approximate intersections that we found from the mesh search. That's the little light green circle on the right. And the yellow circles are the intermediate values that we got from our damped Newton method. And the little teal circle on the left is the final refined intersection we found with an error of less than 10 to the negative 7. And so what you can see is that the final intersection we computed is not at all close to the approximate intersection from the mesh search. In fact, what we found is, if you recall from this picture, we had this line of approximate intersections. And what we found is that all of these intersections, when you differentially correct them, end up at the same final refined intersection. And so essentially, the way to think about this is that in the planar circular three-body problem, the unperturbed problem, you have that heteroclinic connections occur along, not at isolated points, but along curves, right? Because those are trajectories, heteroclinic trajectories in the four-dimensional phase space, since that's an autonomous system. So after the perturbation, of course, you have isolated points, but all the points along that curve are still with a small, when you have a small perturbation, all the points there are still very close to being intersecting, even if not exact. So what our mesh search does is it does pick up some spurious intersections, which then get refined when you do the differential correction. And the reason that you kind of travel along this curve, which forms the intersection in the three-dimensional projections, which you can see here, it's kind of all of these differentially corrected iterations are occurring roughly along this intersection in the 3D projection of the two manifolds, is because in the planar circular problem, all of this is a heteroclinic trajectory. Here, what's happening is that along this direction at each point, roughly tangent to this curve, if you want to call it that, that is almost in the null space of the differential of this left-hand side. So when you do the differential of the left-hand side, multiply its inverse by the error, it can end up giving you a vector that's not close to 0 in that direction. So that's why we have to use a damping in order to prevent it from diverging. So that as you keep iterating, it slowly travels along this curve until you get to an actual intersection. So now just a quick summary of everything and a little discussion of our future work. So we were able to find a Quasi-Newton method to find the unstable invariant tori in periodically perturbed planar circular restricted three-body problem models, and also, of course, managed to use it for continuation after finding some numerical best practices for our method. We computed parametrizations of manifolds and showed that they were significantly more accurate than the linear manifolds that are representations that have generally been used in the past. We showed, of course, that we can use these parametrizations to compute manifolds outside of domains after doing some regularization. And then we were able to use these parametrizations to compute heteroclinic connections using our GPU as well as a damped Newton method. So in the immediate future, our next thing that we want to do is we want to continue the heteroclinic connections by rotation number. So of course, as mentioned earlier, we expect that in these periodically perturbed models, you can have changes of energy by following heteroclinic connections. So here we expect that a single torus should be able to intersect multiple tori in a different family of resonances, rather than only being able to intersect the one at the same energy level as is the case in the planar circular problem. And so after we've finished our entire suite of tools for the periodically perturbed models and applied it to the elliptic problem, we also want to apply this to other models as well, especially restricted four-body models. And we also expect actually that some of these tools should apply very similarly to the spatial circular restricted three-body problem by taking a Poincare map. So that concludes my talk. Just a couple of acknowledgements, of course, JPL, Caltech, and many people, many of whom are here, who have helped me in this work. So, thank you for your
Bhanu.
attention.
Thank you, Bhanu, for your presentation. So now we have the time for questions or comments. You can switch on your camera, Bhanu. Is already switched on?
Okay. Is it off?
Oh, maybe it is on. I don't.
Yeah, it's on.
I don't know.
It should be on.
Okay. Thank you.
Yeah, it's on.
May I ask a question?
Yes, of course.
Well, two actually small ones. The first referring to this increment in the domain, in the principal domain measured in terms of S as K increases, which you showed some transparencies before.
Is it this?
Yeah, probably no. There was something before that you were saying that it was going to 0.01 when K passed from 1 to 5.
Yeah.
Well,
this.
I have just a short comment on that. That first, I would say that it's what is the quantity of real interest here is to measure how far you went from the torus in the original variables, because the S is the parameter. And if you try to say how much you went in the original variable far from the torus in the original variables when you change from 1 to 5, you may find quite surprising results. I recall several years ago, we did a very simple experiment computing manifolds with parametrization in a hyperbolic and non-map. And it turned out that let's say the domain in the parameter was increasing quadratically with the value of K, let's say the order, more or less, the order of the perturbation theory. While when you were mapping this back to the original, let's say how far from the unstable torus I was able to really have computed the manifold, you would figure out that it was only going like the logarithm of K. So you would need exponentially many terms to reach, let's say, a length, an increase by a constant factor in the length in the original variables, not in S. So that's my first comment on that. I don't know if you have ever tried to do this test. I mean, to say how far would you reach, would you improve the distance from the torus by just increasing the order of the parametrization?
See, so by distance, are you referring to like just the distance from Cartesian space from the torus?
Exactly. Okay. Let's say along the unstable direction from the torus. Exactly. Because so, S can be very misleading in that. I mean, S just stretches everything like a straight line, but in reality, that is not so in the original variables.
Right, yeah.
Have you ever tried a test on that?
No, we have not tried that. Yeah, of course, the manifolds can start curving around so that they don't go in a straight line that far away from the torus.
But not even along the direction. I mean, you can just measure it like a continuous variable let's say in the length variable along the manifold. That's what am I referring to. I don't mean the
okay, I see. So you're saying that this is not like an arc length parameterization, essentially.
Exactly. So the parameter gives the impression of representing a length. So let's say, but it is not the same. when you compare to the length parameter along the manifold in the original variables, you get something that goes like the logarithm of s quite often.
I see. Yeah. No, I haven't actually looked at that, but that's a good thing to point out. Thanks for that.
The other question is, okay, you said already that in the elliptic case, we lack, let's say, we fall short one dimension for securing the existence of heteroclinic intersections. So do you have any, let's say, rigorous result or any demonstration type of Melnikov or whatever that these heteroclinic intersections exist altogether?
Sorry, I didn't quite understand. I mean, basically, what the situation we have is that you have these invariant tori with two-dimensional stable and unstable manifolds in four-dimensional phase space when you're considering the stroboscopic map.
Yeah.
So, and we also know that in the unperturbed planar circular problem, that the manifolds intersect along curves.
Right. But this is topologically required in a sense. I mean, if you have curves in a 2D space, in general, they intersect. If you have 2D surfaces in 4D phase space, there is no reason a priori that they should intersect altogether. These are like curves in 3D. They could just bend one inside the other.
Mm-hmm. Yeah, so we haven't quite done like any Melnikov analysis of the heteroclinic connections themselves.
No, but I mean, you can do the implicit function theorem, a constructive version of the implicit function theorem, because you have from the numerical calculations, right? Mm-hmm. You have information about the tangent spaces, right? Mm-hmm. And if the tangent spaces that you have computed intersect approximately, then you know that there is a true intersection there.
Okay.
So, you see what I mean? So you see, you have information about the tangents, right? Mm-hmm. The intersections is, I mean, you have to sort of control the numerical errors, but if you have if you have two planes that intersect transversally, right, then this is not affected. This is a robust situation and is not affected by numerical errors. You see what I mean?
Okay. Okay. Thank you.
So this, I think it's a good idea that could be done a little bit more explicitly, etc. I mean, if you want to be completely rigorous, then you would need to sort of estimate the round of error and so on. But I mean, several people in the audience have done similar calculations, even using CPAD, right? Or CIPD, sorry, CIPD, I always say, right? But the numerical estimates are very, I mean, of course, you can be paranoid and so on, and mathematicians should be paranoid. But from the numerical point of view, it's very clear that the intersections are transversal. Because we have information, I mean, using these polynomials, etc., you have information on the jets, not just on the first derivative, but all the way up to the fourth derivative, right?
Mm-hmm.
Okay, thank you. And are there other questions or comments? I don't hear other people. Okay, so I thank you again, Bhanu, for this nice presentation.
Yeah, thanks for having me.
Thank you, Bhanu. And we will have the next seminar in 2 weeks. The speaker will be Juan Jimeno. And so see you in 2 weeks for the next seminar. Thanks to